Two important developments that questioned the rationality of Bohr's model are: 1. Dual behavior of matter, and 2. Heisenberg uncertainty principle. Let's understand these developments in detail. After the dual behavior of electromagnetic radiation was known, de Broglie proposed in 1924 that all matter has wave and particle-like properties. His theory implied that just like photons, every moving object, be it an electron, a ball, or a planet, has a wave nature. He also gave the relation between wavelength and momentum of a material particle based on the energy equations of photons in their wave and particle forms. A photon displaying wave character has energy equal to h multiplied by nu. A photon having a particle character has energy equal to m multiplied by c raised to the power 2. By combining these two equations and replacing nu with c by lambda, we get lambda is equal to h divided by mc. To generalize the equation for any material particle, c, the velocity of light, is replaced with v, the velocity of the material particle. The resultant equation is called de Broglie's equation. Since the momentum of a particle is the product of its mass and velocity, the relation between wavelength and momentum of a material particle can be given by de Broglie's equation. It can be noted from de Broglie's equation that the wavelength and mass of an object are inversely proportional. That is, that the wavelength of heavier objects is small and vice versa. Thus, the wavelength of lighter particles like electrons can be measured experimentally, whereas that of heavier objects like a ball or a planet cannot be detected. De Broglie's theory and equation was later proved to be correct when it was found that an electron beam undergoes diffraction, a property that is unique to waves. The wave nature of electron forms the basis of an electron microscope that achieves a magnification of about 15 million times, and is therefore a powerful tool in modern scientific research. Let's now look at the Heisenberg uncertainty principle. In 1927, a German physicist, Werner Heisenberg, took forward the concept of dual behavior of matter and radiation to give a principle about the uncertainties in simultaneous measurements of position and momentum of small particles. He proposed that it is impossible to measure simultaneously and accurately the exact position and momentum of a small particle like an electron. Mathematically, Heisenberg's uncertainty principle can be expressed with the equation delta x multiplied by delta px is greater than or equal to h divided by 4 pi, where delta x is the uncertainty in position and delta px is the uncertainty in the momentum of the particle. This equation can also be expressed in terms of mass and velocity of the particle. Note that the uncertainty in the position and velocity are inversely proportional to each other. This means that if the position of the electron is known with high degree of accuracy, then the velocity of the electron will be uncertain and vice versa. Also note that the uncertainty in the position and velocity are inversely proportional to the mass of the object. That is, uncertainty in the position and velocity decreases as the mass of the object increases, and vice versa. For example, if the uncertainty principle is applied to a macroscopic object, an object weighing a milligram 10 to the power 6 kg, the value of the product of delta V and delta X is extremely small. Therefore, the associated uncertainty is also insignificant. On applying this uncertainty principle to a microscopic particle, like an electron having mass equal to 9.1 multiplied by 10 to the power minus 31, we find that the product of delta V and delta X is significant enough and therefore cannot be ignored. Hence, we see that Heisenberg's uncertainty principle also holds significance only for motion of microscopic particles and not for macroscopic objects. The position of an electron can be determined experimentally by illuminating it with electromagnetic radiation having a wavelength smaller than the dimensions of an electron. However, the velocity of an illuminated electron cannot be detected as the high momentum photons of the light increase the energy of electrons by collisions. As we have already calculated that for an electron, the product of delta X and delta V is found to be equal to 10 raised to the power minus 4 square meters per second. Therefore, the uncertainty in velocity can be calculated by substituting the value for delta X, say 10 to the power minus 8 meters, in the Heisenberg's equation. This means that if one tries to find the exact location of the electron to an uncertainty of only 10 to the power minus 8 meters, the uncertainty in velocity becomes positive and enormously significant. This value of uncertainty in velocity is so big that the classical picture of electrons moving in Bohr's orbits becomes unrealistic. As it is impossible to determine simultaneously and accurately the position and velocity for an electron at any given instant, it is not possible to talk about the trajectory of an electron. Thus, Bohr's model not only ignores dual nature of matter, but also contradicts the Heisenberg's uncertainty principle. Due to these inherent weaknesses in the Bohr's model, a need for such an atomic model arose which could account not only for the dual nature of electrons, but also be consistent with the Heisenberg uncertainty principle. This search led to the advent of quantum mechanics.
Hello guys, now the development leading to Bohr model, and in this one, first of all, Newton suggested that matter is particle in nature, and he has given particulate theory, and according to that, reflection and rarefaction has been explained, but its limitation are those interference and diffraction he could not explain. Then after that, J.C. Maxwell came. He suggested that matter is wave. Then he has given the explanation of interference and diffraction but he could not explain the photoelectric effect and black body radiation. So, whenever J.C. Maxwell, then after that, and the wave is attached with the electric and magnetic field both. On the behalf of this one, J.C. Maxwell in 1856 has given the electromagnetic wave theory. And some point of this one is that energy is emitted from a source continuously in the form of electromagnetic radiation or wave. Like as sun energy is coming toward us, it travels with the velocity of light, that is 3 into 10 power 8 meter per second, and these waves are oscillating electric and magnetic field that I told you, and they do not require any material medium. They do not require medium for their propagation. They can come from no requirement of the medium. So they can come in the vacuum also. Then he had given some characters of the electromagnetic wave theory. Number one is that he has given that this is what the wavelength and frequency, that is nu 1 by t, that is what called cycle per second, and its unit is what hertz. Then he has given the formula of wave number, that is nu bar is equal to 1 by t. Then he has given the relation between wavelength, frequency and velocity. C is equal to nu lambda. From this, nu is equal to c by lambda you can find out. And amplitude, height of the crest or the depth of the trough. That was the major things of the electromagnetic wave theory. Then after that, he has explained the diffraction and rarefaction, photoelectric effect and black body radiation, that was given by the Planck theory, Planck constant. After that, Planck theory come into the existence, and then dual nature, de Broglie in 1919. First, Newton came. He told that matter is particulate in nature, and he has explained reflection and rarefaction. Its drawback are what? Interference and difference. Then after that, Maxwell came. He has taken the matter is in a wave, and wave is attached with the electric and magnetic field. He had explained interference and diffraction, and its drawback is what? Photoelectric effect and black body. Then Planck has came into action in 1919. Planck theory, Planck came, and Planck also told that matter is particle in nature, and on the behalf of particulate nature, he has explained the photoelectric effect and black body radiation, that we will take in the next class. Thank you, dear students.
For atomic model is very important from the examination point of view. Lots of questions are asked from it. So I will suggest students to know about the Thomson Plum-Poding model as well as the Rutherford atomic model, and thereafter comes to the Bohr's atomic model, because that will give a clear idea about the Bohr's atomic model. There was a flaw in the Rutherford atomic model, and that was the electrons, those electrons who are moving in a circular orbit around the nucleus will emit energy in the form of radiation, and eventually it will collapse to the nucleus by emitting radiation. and making the atom unstable. But actually it is not so. Atom is stable in normal case, so there must be flaw in the Rutherford atomic model, and that flaw has been removed by the Bohr's atomic model. So there are some postulates of the Bohr's, and let's start from the first postulates. The first postulate say an atom has a very small positively charged nucleus. Almost the entire mass of the atom is concentrated in the nucleus. That means that the large uh, portion of the atom is empty, and the whole mass, nearly whole mass, is concentrated in the nucleus, because there are three fundamental particles, you know very well. One is electron, one is proton, and one is neutron. Proton and neutron, those are heaviest particle and remains at the center, that is nucleus. And electrons are very lighter particles that revolves around the nucleus in an orbit. These orbits are known as a stationary orbit. Whatever things to remember is that the size of the atom is of the order of 10 to the power minus 10 meter, and size of the nucleus is of the order of 10 to the power minus 14 meter. Okay, 10 to the power minus 15 meter is also written in some books. And here there is a picture of an atom showing an electron moving in the orbit around the nucleus, in which there is a positive charge Ze. Z is the atomic number and E is the electronic charge. It's a positive charge nucleus, and this is the electron which is negatively charged. Now the next is second postulates. What does second postulate say? Electrons in an atom revolves around the nucleus in certain permitted non-radiating stationary circular orbits. Here these words written in green colors and yellow colors or orange colors must be remembered by the students, because these words have a very important meaning. And here stationary, earlier I have told you that stationary means the orbit will have an energy level, a fixed energy level, and in which the electron will not lose energy. Okay, electron will have a fixed energy if it is rotating, if it is revolving in that orbit. Okay, so it here non-radiating term has been mentioned over here. If it is moving in a circular orbit, there must be a centripetal force, just like this one. If it is moving in a circular path, an electron has a velocity v in the tangent direction. Okay, so it must have a centripetal force, and centripetal force here is provided by the electrostatic force of attraction between the two unlike charges. One is at the center, that is Ze plus charge, and the other is at the orbit where the electron is at any instant, and it has a negative charge. Okay, that is here, if I could write over here, the electrostatic force is equal to the centripetal force. Next is electron can revolve only in that orbit in which the angular momentum of the electron is integral multiple of h by 2 pi. Now what is angular momentum? Angular momentum is just the multiplication of the linear momentum with the radius. Okay, the mv is the linear momentum, and this is the when multiplied by r radius will give the angular momentum. Okay, and this is equal to ns by 2 pi. What does n is a number, and it's an integral number. It can have a value 1 2 3 4 etc, whatever. And h is the Planck constant. It has a value 6.62 into 10 to the minus 34 joule second. Okay, and n cannot have a fraction value. That's why it has been told integral multiple of h by 2 pi. Okay, and this condition is known as the quantization condition on the angular momentum of electron. Why quantization condition? Because only some fixed radius are permissible, and this is why the angular momentum is fixed, because this full term in the right side is a fixed quantity for a certain number of orbit. Suppose for n is equal to 1, this will be equal to h by 2 pi. For n is equal to 2, this will be equal to 2 into h by 2 pi. For n is equal to 3, this will be equal to 3 into h by 2 pi. So it will have a fixed value. So the angular momentum will also have a fixed value for first orbit, for second orbit, for third orbit, and so on. That's why it when something is fixed, it is called quantization, and that's why it is called the quantization condition on the angular momentum of electron. N is also known as the principal quantum number. N is also known as principal quantum number. Okay, and so far the maximum value of maximum known value of n is 7. Okay, theoretically it could have a value infinity, but practically the maximum value is 7. Next, the third postulate. Third postulate says whenever electron jumps from higher orbit to lower orbit, it loses energy in the form of electromagnetic radiation. And by absorbing a quantum of energy, the electron jumps from lower orbit to higher orbit. That means, let us suppose this is a picture of the atom, and here the 4 orbit has been shown. The first orbit is n is equal to 1, second n is equal to 2, third is n is equal to 3, n is equal to 4. And whenever any electron from lower orbit, suppose here in this case n is equal to 1, here the electron moves from first orbit to third orbit, but it moves from first or third orbit only when it absorbs some quantum of energy. Here the quantum of energy is equal to h nu, where nu is the frequency and h is the Planck constant. Similarly, from higher orbit, the electron jumps from higher orbit to lower orbit. It could jump from n is equal to 4 to n is equal to 3, n is equal to 4 to n is equal to 2, n is equal to 4 to n is equal to 1, whatever. And this way it releases energy, and that released energy will be equal to the difference of the energy level. So the mathematical expression is En2 minus En1 is equal to h nu, where nu can be written like this, c by lambda, where c has a value 3 into 10 to the power 8 meter per second, which is the velocity of light, and lambda is a wavelength. This is the final energy level, this is the initial energy level. Okay, and this n is equal to 1 state is called ground state. This n is equal to 1 is equal to called ground state. And whenever an electron is removed from first orbit to infinity, that means the electron is just pulled out of the atom. In that case, the amount of energy required is known as the annihilation potential. Okay, so that's the 3 postulates of the Bohr's atomic model. I think you will like it, and just mention if there is any problem in understanding, and I will try to improve myself. And just share it with your friends so that they will also get benefited from my lecture.